All right, if you've ever wondered where the real journey into calculus begins, well, you're in the right place. Today, we're diving into limits, the one concept that, honestly, everything else is built on. So yeah, let's get into it.
But first, let's start with a bit of a puzzle. Your car's speedometer says you're going 60 miles per hour. Okay, but what does that actually mean for one single frozen moment in time? In that exact instant, no time has passed and you haven't traveled any distance. So how can you even have a speed? It sounds like a total paradox, right? Well, the answer is hiding inside this idea of limits. And that really gets to the core idea here. A limit isn't about being exactly at a point. No, it's all about the approach. It's this art of getting infinitely, ridiculously close to a point from either side and just watching to see what happens.
So here's the more formal way to say it. A limit is the value, let's just call it L, that a function f of x gets closer and closer to as our input x gets closer and closer to some number c. The key word here, and you're going to hear it a lot, is approaches. It's all about the trend. As you can see on a graph, while our x is scooting closer to c on the bottom axis, the function's value, f of x, is zeroing in on L on the vertical axis. We're watching where it's going, not where it lands.
Now, as you'd expect, mathematicians have a very specific, kind of elegant way of writing all this down. Getting a handle on this notation is super important because it's the language we're going to use for this whole process.
And this is what it looks like. We read this out loud as the limit of f of x as x approaches c equals L. So let's break that down real quick. X is our input, the thing we're fiddling with. C is our target number. F of x is our function, the machine that spits out an answer. And L is that final value that our output is heading towards.
Okay, but here's a really crucial detail. The direction you come from matters a lot. We can sneak up on our target C from the left side, using numbers that are just a little bit smaller. Or we can come in from the right, using numbers that are just a tiny bit bigger. We call these one-sided limits, and they are absolutely critical for what comes next.
And this is the golden rule. If there's one thing to remember, it's this. For the overall limit to actually exist, the journey has to lead to the exact same destination no matter which side you start from. If the left-hand limit and the right-hand limit are the same, boom, you've got a limit. If they're not, you don't. It's that simple. All right, now that we have the rules and the lingo down, let's actually put this into practice. We're going to look at 3 super common puzzles or scenarios that you're pretty much guaranteed to run into when you're solving for limits.
So our first puzzle, this is what I call the straightforward path. We're trying to find the limit of the function 2x plus 3 as x gets closer and closer to 2. This is the kind you hope for on a test, right? It's just a nice, simple, continuous line with no funny business.
For functions like this one, where there are no gaps or jumps, the answer is, well, incredibly simple. All we have to do is something called direct substitution. We literally just plug our target value, 2, right into the function for x. So we get 2 times 2, which is 4, plus 3, and that gives us 7. That's it. The limit is 7. Easy enough.
Okay, puzzle number 1 was just the warm-up. Now, let's try something a little trickier. We want to find the limit of this fraction as x approaches 2. But if you try to just plug 2 straight in like we did last time, you get 2 squared minus 4 on top, which is 0, and 2 minus 2 on the bottom, which is also 0.
So you end up with 0 divided by 0. Now, this is called an indeterminate form, and it's not a dead end. It's actually a huge clue. It's the math telling you, hey, you need to do a little more work here. So let's look at the top, x squared minus 4. We can factor that out, right? Into x minus 2 times x plus 2. And look at that. We have an x minus 2 on top and an x minus 2 on the bottom. We can just cancel them out. Now we're left with the much friendlier function x plus 2, and if we plug our target value of 2 into that, we get 4. The limit is 4. This is a perfect example of how the limit is what the function approaches, even if it's technically broken right at that exact point.
And for our last puzzle, we've got a piecewise function. This is basically a function with a split personality. It follows different rules for different x values. Let's say our function is x plus 1 for all the numbers less than 0, but it's x minus 1 for all the numbers greater than or equal to 0. So what's the limit as x approaches that crossover point, 0?
This is where that golden rule becomes everything. We have to check both sides. So first, let's come from the left. For values just under 0, the rule is x plus 1. So as x gets closer and closer to 0, x plus 1 gets closer and closer to 1.
The left-hand limit is 1. Okay. Now from the right, for values just above 0, the rule is x minus 1. As x gets close to 0, x minus 1 gets close to negative 1. The right-hand limit is negative 1. So, does 1 equal negative 1? Nope, they don't match. So we have to conclude that the overall limit does not exist, or as you'll often see, DNE.
So now that we've worked through those puzzles, let's do a super quick recap of the common mistakes that trip people up. Just think of this as your cheat sheet for success.
First off, always remember, the limit is about the journey, the approach, not the final destination. A function can have a hole at a certain point, but the limit can still exist there. Second big one, if you get 0 over 0, do not stop and write 0. It's a signal to do more algebra, usually factoring and canceling. And finally, and I can't stress this enough, if you see any kind of function with a jump or a break in it, you always have to check the limit from both the left and the right.
Okay, so we've been through the theory, we've done the mechanics, but why does any of this abstract stuff really matter? Well, let's bring it all the way back to that real-world puzzle we started with.
Remember this number? That reading on your speedometer, your speed at one single frozen moment in time. And here it is, the big aha moment. Instantaneous velocity isn't just a number, it is defined as a limit. It's the limit of your average speed, distance divided by time, as that little slice of time gets infinitely small, shrinking all the way down towards 0. So it's not a paradox at all, it's literally calculus in action.
And that's really the bottom line here. Getting good at limits isn't just about passing the next test. It's about understanding the one idea that unlocks the rest of calculus. It's the foundation for derivatives, which measure how things change, and for integrals, which measure how things add up. It is truly the bedrock of everything.
So, I'll leave you with this to think about. We just used this idea of getting infinitely close to a point to perfectly define a single instant in time. Where else, maybe in science or engineering or even economics, where else might this powerful idea of approaching something without ever quite touching it completely change how we see the world? It's a pretty cool thought.